we are going to solve the differential equations we obtained, linearized differential equations. So we start considering the motion in the g directions. In the g directions, equation is a really simple one. This equation. Then we'd like to find the second derivatives. So to calculate the second derivatives, you need to calculate the first derivatives. U is expressed minus 1 over 2 omega squares x square plus y square minus g m sub 1 over r sub 1 minus g m sub 2 over r sub 2. And r sub 1 is expressed square root and r sub 2. Then round u, round z is becomes g m sub 1 over r sub 1 cube g plus g m sub 2 r sub 2 cube g. Partial derivative of u with respect to x, we have these equations. Then we'd like to calculate the second derivatives. You can get these equations. Then you need to substitute Lagrange point. At the Lagrange point, z is 0. So you can substitute z equals 0. Then you can find this term. This term is both positive. Second derivative of u with respect to g is a positive quantity. Then this is a positive quantity. Then it becomes oscillational motion. Then especially the motion in the g direction at the L sub 4 and L sub 5. You can substitute at the L sub 4, L sub 5, M sub 1, M sub 2, and the Lagrange point is located here. This is R sub 1, R sub 2, R sub 1, 2. So this is 60 degrees, 60 degrees, 60 degrees. So you need to substitute this quantity. So it becomes next line, this one. Then this is exactly equal to the omega squares. Then frequency of the motion in the g direction is equal to the rotational frequency of m sub 2 with respect to the m sub 1. Okay. Then equations. We don't have to consider the equation in the d directions. We only consider the motion on the xy planes. So we have two equations. And the a, b, c is just constant values. We calculate the second derivative, partial derivative with respect to x, and then substitute Lagrange point. Is a partial derivative of u with respect to x and y. This is b. And c is a second order partial derivative with respect to y, and substitute Lagrange point is c. Okay. Then to calculate the second derivatives, so we start with this u and substitute. So I'd like to show you the first derivative at first. Round u, round x can be calculated. Minus omega square x plus g m sub 1 over r sub 1 cube x plus nu r sub 1 2 plus g m sub 2 over r sub 2 cube x minus 1 minus nu r sub 1 2. Okay, this is the first derivative with respect to x also round u round y can be calculated minus omega square y plus gm sub 1 over r sub 1 cube y plus gm sub 2 over r sub 2 cube y. So we can calculate first derivative. Then one more derivative we need to calculate to find the second derivative. So second derivative, we have three equations. For the second derivative with respect to x, and second derivative with respect to x and y, and second derivative with respect to y we could calculate. Then if you substitute Lagrange point, we could discover that this A, B, C's, okay, at each point. So we could discover the A, B, C's. And the equation is a second order differential equation. But to solve the higher order differential equation, this is a kind of technique when you're solving the differential equation. We have to reduce the equation into the first order differential equations. So this is second order. To the first order, we'd like to transform the differential equation, second order differential equation to the first order. We need to introduce the new variables. So this is how to find out the equations in the matrix forms. So last case we have only the x and the y as a dependent variables, and the independent variables is a t. So we extend the dependent variables as the two more dependent variables, x dot, y dot. So these four is the dependent variables we consider. So if you introduce the vectors x equal x, y, component x, y, x dot, y dot, then this matrix forms differential equation using the matrix x dot equal ax, and this becomes a first order differential equation, and the A is a 4x4 constant matrix. Then how to solve this equation? This first equation is a really complicated equation, and we'd like to transform the matrix. Then if we happen to transform the equation into the next lines, P dot Q dot R dot S dot equal a matrix times P Q R S. Then actually we have four equations. So from the first equation we have a P dot equal lambda sub 1 P, Q dot equal lambda sub 2 Q, R dot equal lambda sub 3 R, S dot equal lambda sub 4 S. So equation becomes independent with each other. Then we'd like to solve these equations. So for example, first equation. So P dot equal lambda sub 1 P. So this means dP dt equal lambda sub 1 P. So this means dP over P equal lambda sub 1 dt. They integrate in the both sides. Log P is a lambda sub 1 t plus integration constant. So this means P is expressed P sub 0 exponential lambda sub 1 t. Actually P sub 0 is equal to the exponential c. When lambda sub 1 is a positive, then P is go to the increasing toward infinities. So this means P is go to the increasing to the infinities. So this corresponds to the unstable mode. Okay, so once you could transform this equation, we could easily solve the equations. Okay, this is the end of this session.